Welcome to the second keynote speech. I'm really pleased to introduce you to Professor Peter Atkinson, Distinguished Professor and Dean of Social Science and Technology at Lancaster University. So we're thrilled that he agreed to come today to give us a talk. And the talk is about a novel paradigm for the simultaneous land use and land cover classification. So without further ado, I'll pass you over to Peter.
Thanks very much for inviting me. Thanks to Scott. Thanks for the introduction. And also thanks to Cardiff University. It's easy to forget where we are in a sense because the conference is virtual, but it is Cardiff University that's organising the GISRUK, and from what Scott was saying, doing a great job. So thank you to Cardiff. So this talk is about a thing called joint deep learning. Everybody may have heard of deep learning. This is something that builds on deep learning into something slightly different. A novel paradigm for simultaneous land use and land cover classification. The word paradigm here is pretty heavy and perhaps not justified, but certainly the word concept would be appropriate. And it's the concept that I want to emphasize, really, because I think often in research in spatial data sciences, the concepts that are key. So this is a talk as part of a series sponsored by the International Association for Mathematical Geosciences, because most of the talks I've given are virtual, then the sponsoring wasn't really necessary. But nevertheless, the IAMG selected me as a distinguished lecturer for 2020. And as a result, I just wanted to introduce you to the IAMG that this lecture is part of. The IAMG is just a scientific organization that does two things, really. It does meetings, organizes meetings, and it has a series of publications. And a third thing there, cooperation with other organizations. But basically, it's just the usual kind of scientific society. On the left here, you can see several journals that it's involved in. Mathematicalgeosciences is a long-standing journal since 1968, I think. Computers and Geosciences includes oftentimes program code, and natural resources research and applied computing and geosciences are also in that stable. And then the IAMG also produces a very nice newsletter that's very well put together and so on. So if you're interested in geology or earth sciences more generally, then this might be of interest to you. Have a look. I also wanted to say something about Lancaster University. So I'm the Dean of Science and Technology at Lancaster University and was also the Dean of Health and Medicine there for a year. It's a fantastic university, one of the world's great universities, I think. It's placed in a really attractive position in the northwest of England. You can see from the countryside around that the quality of life around this area is pretty good. And it's a campus-based university, so there's lots of interaction, and the interdisciplinary research that goes on there is second to none. Interestingly, I did a keynote talk at Lancaster before I joined Lancaster 6 years ago, and that talk was titled Space-Time Modeling of Environmental Data, and the talk I'm giving today is kind of similar, but it doesn't have the time element. It's just spatial modeling of environmental data. So it's interesting to have been invited to Lancaster and then be giving a talk from Lancaster. So I'm going to do two things by way of introduction, and I hope this is okay and you can bear with me. The first is a sort of general introduction to the area and the field. The second is a more of a sort of foray into representations in geographical information science, and it's not really necessary for this talk to do it, but I wanted to do it because I think this idea of representations is super important, and we all need to be, asking ourselves questions about representations. So the first part then is just a general introduction to the topic, and I'm covering data, methods, and methodology as a way of combining data and methods together in order to answer a question. And just to sort of think about some of the things that are occurring in the world at the moment in terms of data, we've got these kind of space-time stacks that I talked about in 2012 in terms of being able to answer questions for monitoring. These are shown on the top left side here. Monitoring we can do in remote sensing that we were not able to do initially in remote sensing, because it took a long time to get these kinds of stacks that we get from MODIS and MERIS and sensors like that from the Landsat archive. Now goes back a long time, etc. Monitoring, also using these data to infer dynamics through process models, that sort of thing. Those are very much the sort of standard now in remote sensing. We also have data from point clouds that, in a sense, are a different representation. There are many things occurring in terms of representations in point clouds that make them different, and therefore require different approaches and different methods to handle those kinds of data, but opening up lots of possibilities. And also the kind of volunteered geographic information or crowdsourced data that Mike Goodchild introduced nearly 20, the concept that Mike introduced 20 years ago has really taken off, as everybody knows. And also data streaming has become very important in terms of being able to handle data in real time and so on. So these are the sorts of things that are interesting and occurring at the moment. I wanted to make a point about these global types of data products that are available, and the utility of those, and also sort of express a certain amount of guilt about using them. As a remote sensor, having spent quite a bit of my life thinking about how to process raw remotely sensed imagery representing radiance to reflectance, and then do sort of geometric corrections and atmospheric corrections, and then some kind of regression model, classification model in order to make a product. You spend quite a lot of your life working out what are the best methodologies in order to make the best products. Well, of course, there are efforts across the globe to make standardized data sets and products through various organizations that are potentially very useful in a science context. And I would say, in relation to these data products, of course, you have to be very mindful of the processing that went into producing those in the first place, and have a whole lot of caveats around the use of those data, because there are implications in terms of the nature of the data, the nature of the accuracy in those data, etc. But with those caveats and with those conditions, then I would say go ahead and use those data to answer science questions, and they open up a huge window of opportunity to do that. So I wanted to flag those kinds of data sets that have become available. There are many out there, including GlobeCover, which has a 300-meter resolution, which is produced by ESA between, forgotten the first date, but it goes up until 2015, I think. And also to flag this emerging data set, which is produced by Google, the World Resources Institute, and also, although I couldn't see it mentioned here, National Geographic, with people like Steve Brumby, who's mentioned there at the bottom from the Impact Observatory, producing global data at a 10-meter resolution using Sentinel products, Sentinel imagery. Those kinds of data are transforming what's possible in terms of answering scientific questions that we might want to ask. So if we switch from data to methods, I just wanted to mention some things that are very commonly talked about these days. So machine learning is one of them. This representation here suggests that we provide an input and we get an output. And in the middle of that, we do some feature extraction, which really means transforming the input data so that they're suitable as an input to the classifier, and then running the features that are extracted through the classifier or the regression model. It could be classification regression. It could be some other operation that we want to do. For example, optimization of a sampling design, or it's not only classification that we want to do with these kinds of methods. But classification is an example, and in this case, the output is binary; it's car or not car. So machine learning is everywhere at the moment. Lots of people interested in using those and making applications out of it. The other two that I've got down the bottom here are, on the left-hand side, Gaussian processes, and having a geostatistical background. I see the sort of commonality. very, very close, if not identical, overlap in some regards between geostatistics and Gaussian processes. But this representation is interesting. It, for me, represents the expectation of a random field, and the Gaussian process, in the sense, or random field, is really the spatial the spatial equivalent of a random variable. So if we had a single point, we would have a random variable, so a distribution, like a, represented through a PDF or a cumulative distribution function or something like that. In the case of Gaussian processes or random fields in geostatistics, we've got effectively the spatial equivalent of that. So what you see here would be the expectation, and although it's very difficult to represent and not represented here, you would expect to see some distribution around the upper part and the lower part below and above the surface that's represented here. And the idea is that if we can fit one of these two spatial data, then we are able to interpolate, in other words, to identify what to predict at places where we don't have the data, which becomes obvious when you see this kind of representation. The Gaussian processes are also everywhere. So machine learning is everywhere. Gaussian processes are everywhere. I would say that we need to exercise some caution with Gaussian processes, because the world doesn't always look like that. And if you use Gaussian processes to simulate, you'll find that the simulations usually don't look very much like anything in the real world, except where you've got atmospheric processes or things that are more fluid. Some kind of fluid, like in water or in the atmosphere. But on the land surface, there's very few things that actually can be simulated well with a Gaussian processor. So we do need to exercise caution there in their application. And the third diagram that I've got here is really representing Bayesian inference. And one point that I wanted to make is that everybody's using Bayesian inference, but it is an inference method. It's not a model as such in itself. It's a method of fitting models to data, and it has advantages. For example, being able to set priors does allow one to knit to fit things together that would otherwise be difficult to fit. Not sure I've got another point to make about that. Other than these three things are kind of becoming very common in spatial data science and environmental data science. And here are some things that are sort of emerging at the moment. Not all methods, actually. One is deep learning, which I'm talking about, and it has become ubiquitous. Everybody's doing deep learning as well as machine learning. And I suppose my way of thinking about deep learning is that the way that this diagram represents deep learning is to say the feature extraction, the transforms that you'd have to do on the input data are done within the deep learning machine. Fine. But for me, the thing that distinguishes deep learning really is the fact that you're trying to predict higher order representations, which it's difficult for, say, an MLP type algorithm to do. So in a land cover land use situation, things like trying to predict it's a train station, for example, would be very difficult to do if you weren't using a deep learning approach. To predict something like it's a golf course would be difficult to do, because it's a very high order representation. I'll come on to that a little bit more when I get through the detail of the talk. The other thing is that the deep learning methods, like a convolutional neural network, use a patch as an input, and that means that you're basically throwing spatial data and spatial information directly into the machine. And we've known for a long time, a huge number of years in remote sensing, that it was difficult to predict land use directly from pixels, and you needed context around the pixel in order to predict land use. And the reason for that is exactly the same as the reason that deep learning is able to predict higher order representations. It's the land use is a slightly higher order representation than land cover. Land use represents the function of the land, whereas land cover represents the state of the land. So by taking a patch and using that as input to the machine, like a convolutional neural network, you're able to predict higher order representations. That's really key in this talk. The other things I wanted to point attention to were explainable AI. This seems to be the hot topic at the moment. Deep learning is saturated. If you look at the number of citations around deep learning, they're saturating, whereas XAI is on a steep rise at the moment. And there are many different ways of thinking about the meaning of XAI, but it is a hot topic at the moment. So that's where I would be paying attention. The other thing here is to go back to point clouds again and say that a lot of these techniques that are being developed, like deep learning and XAI, they're more difficult to apply to point cloud type data than they are to images. And so there is a rich field of inquiry around being able to do that at the moment. Okay, so this is like going back to Spatial Data Science 101, but I wanted to put it in there. It's therapeutic more than anything, I think, is that having spoken about data and methods, obviously we need to put those together in what's called a methodology that's in that sense different to methods. We have data input A goes to tool X, and that produces data B. Data C is added to that through tool Y, and we produce an output which is data D. And we would call that a methodology. I did an interview with Peter Diggle, a famous statistician at Lancaster University in 2019, and published that in Statistical Science. It's a great read, actually. Sorry, I shouldn't say that, but it's a great read, and Peter did a fantastic job. His ability to talk off the cuff in very precise terms is just incredible. But one of the things he came out with was don't analyze data, analyze problems. And I couldn't agree with that more. That methodology that I showed is shown at the bottom here is pretty meaningless unless we've asked the right question in the first place. So yes, we need to ask a question that requires data D to answer it. If we can do that, then fine. But we need to pay attention to what is the most important question. And in research, for those of you that are doing PhDs or as a postdoc, there's such an important point to reflect and think what is actually the most important question to be answering. And this is my final slide on this sort of 101 introduction. In environmental data science, there are two main research methodologies, and I can see Scott glaring at me at the moment. What? You can't say that. But anyway, if we think about the science side, not the social science side, then we've got two research methodologies mainly, and of course these bifurcate into lots of different research methodologies. But basically, science and engineering. Science is usually not always, but usually some kind of experiment against control in order to reach an inescapable conclusion. And engineering is design, where you're able to demonstrate through benchmarking that one method is in some sense, in some dimension, better than another method, again, allowing you to reach an inescapable conclusion. And this talk is going to be focusing mainly on the engineering research methodology, in other words, design of a technique to do something. So this is the bit where I go off on a tangent, so bear with me. So this is the bit where I talk about representations. Companies like Amazon, Google, and eBay do a lot of machine learning, deep learning, Bayesian deep learning, etc. And the reason that they're successful, I think, in part, is because they're dealing with humans, and humans don't have measurements about human decisions and don't have a support in this. And I hesitated there because I have to introduce the concept of support. But support means the space over which a measurement is made. And in the environment, generally, I would say ubiquitously, measurements have a support. In other words, they're an integral of something over a definite fixed space. Whereas for these companies, they don't have that problem at all. And what you type into the computer is the answer without a support. That means that the data are the reality in a sense, and the data can be analyzed directly. But in environmental data science, that's not the case. So, Nick, if you're out there, I'd give a nod to our 2000 paper called Spatial Scale Problems and Geostatistical Solutions. And more recently, I did a paper with various authors here in 2019, which extended what Nick and I did in 2000. This one was published in Earth Science Reviews, and I'll just briefly I'll basically just briefly go through these the key points of these papers as a background to this paper that I'm presenting today. So, starting with states, which is what Nick and I were basically focusing on, we made the point that data for environmental, in the environmental case, are a function of two things. They're a function of reality that you're really interested in, and the sampling framework, and that's ubiquitous. It's always the case, but people forget it. So when we think about data science, the tendency is to go and analyze the data directly. But in a principle, if you think about this from a principal point of view, the sampling framework is always there and represented in the data. It always affects the data. So if you zoom in and come close to the screen, you'll see things that you didn't when things, even though the phenomenon that you're interested in is the same. So the sampling framework is clearly there always, and it's influencing the data. So you can't analyze the data directly. You've got to consider the sampling framework if you're interested in nominally this thing that is, out there, reality, that is the sort of first principle of science, in a sense, to acknowledge that there's an external reality. And the second point is that if reality is going through a sampling framework in order to produce data, then there's a measurement error that's added somewhere there. And the Earth Sciences Review paper talks a little bit about processes, and this is the idea of dynamics that are occurring as a set of kind of rules that tick over through time that lead to changes in the states to produce patterns and so on. So I said a little bit about sampling framework. Let's dig into that a bit. There's more to it than you think. There are three dimensions that I've indicated here: the support, which is the space on which a measurement is made; the sampling scheme, for example, we're all familiar with random, stratified random, and so on. That would be the sampling scheme. In other words, the pattern or the arrangements of the observations themselves. And then the extent, as in the outer limit of the region that you're interested in. And each of those has about 3 or 4 parameters to define them. So you could say that there are 12 parameters that define a two-dimensional sampling scheme. But we don't really consider that all of those things, those 12 parameters, when we're analyzing data. We just go ahead and analyze the data. And this is just a repeat of what I just said, which is that we need to consider that measurement error is incurred per observation when we measure. So the support is an interesting concept. We probably don't think about it very much. The space on which an observation is defined. There are lots of kinds of geographical analysis that are done where the support is important, none more so than the change of support that occurs when we're doing geostatistical analysis. This diagram at the bottom probably overcomplicates it. It just makes the point that in remote sensing we think about the pixel as the support, the space on which an observation is defined. In fact, the measurement is made on a space that's slightly different. It's center weighted like a bell shape, called a point spread function, and then we allocate the measurement that we've made on that point spread function shaped support to a pixel. Again, we often don't think about these kinds of concepts when we're doing data science. This really it just sort of returns to the point about measurement error and says where I think measurement error probably occurs in the sequence that goes from reality to sampling framework to data. But the key through all of this is that geospatial data science, the key is representations. Now, all of that was bad enough, and sorry to sort of go off on that tangent and ask for your attention through that, but it gets a little bit worse because there are that simple representation about what's going on that Nick and I did in 2000, and others have done it before us, Bloch and Savalapan and others. It's much more complicated than that, actually. We have to frame our measurement process, and we do that by defining a space. So it could be continuous Euclidean, or it could be two-dimensional, three-dimensional, four-dimensional. It could be also discretized or non-discretized. So we define a space, then we have a data model, raster, object, continuous random field, object, point, etc. And then we have a data type. So it could be, when we do the measurement, it could be a binary, it could be a continuous measurement, and so on. So it's all of these things are going on. When we use our brains to look at the environment, a lot of these things are being invoked without us even thinking about it. When we measure formally in science, we need to be aware of and record these decisions that were being made. Probably we do them. We're just not as formal about them as we should be. And if we were more formal about them, I think we'd see more clearly what's going on. The other thing to say is that that reality probably needs to move from where I had it before to before all of this occurs. And of course, we never actually touch reality. We only touch data. So whether reality is really out there or not is a completely different and more and deeper question for somebody else. But it probably sits to the left of this sequence anyway. Model on the right-hand side implies that we're applying some kind of stochastic or other type of model to the data once we've observed them. Right, so let's move on to a couple of case studies then. And thanks for bearing with me while I did that. The reason for doing it should become a little bit clear. So case study one, what's the statement of the problem? Well, we were interested in CNNs and deep learning, these convolutional neural networks. We were interested in those, but they were generally designed to predict high-level representations, like to say, it's a cat or it's a dog. So it would be presented with a patch, and it would be asked to say, what is it in the patch? And we felt that wasn't really appropriate to be applied directly to remotely sensed images. So we wanted to, we could see that there was potential value there, especially this ability to predict high-level representations. But we wanted to make sure that we wanted to ask the question: is if it's appropriate, what's the appropriate use of deep learning in remote sensing? And if it's not directly applicable, then how can we change it so that it's more applicable or directly applicable? And just to say that you can probably tell from what I've said there in terms of design questions that this is not science as such. This is engineering research methodology, given what I said earlier. So this was published in 2018, so very early on in the in the sense of applying CNNs or deep learning to remote sensing. So rapidly out of date, I'm afraid, but nevertheless an important precursor to what I'm going to say as a second case study. So I'm going to go through it. So to aid us in designing what would be an appropriate use of a CNN, application of a CNN to remote sensing, we basically thought remote sensed images are generally a mosaic of land covers or land uses. They're not like it's a cat in an image with a background. That's not true for remote sensed images. The whole space is covered, and generally there's a mosaic of things going on, like agricultural fields or in a patchwork, or the urban environment is made up of gardens and houses, etc. So it's generally a mosaic, which makes it different. And often, but not always, but often, what we're interested in within a remotely sensed image is objects, and those objects have a very large distribution of different sizes, and they're arranged in different patterns, etc. So we needed to think about, well, how are we going to adapt this deep learning type of approach so that it's applicable directly to remotely sensed images? So we'd already done some work with segmentation. So that was a straightforward step to segment the image first in order to create objects. And this has the advantage, of course, of being able to retain boundaries, because when a CNN is presented with a patch and it says it's a cat, it doesn't, I mean, they can now through different kinds of neural networks, but the original CNN at the time didn't define a boundary for the label. So we wanted to retain the boundaries, and we also wanted to know where should we put the patch within or across those objects in order to do the best job. And then we needed a method of allocating a single label to the object, given if there were multiple patches that were placed across that object. So we came up with this methodology. I'm not sure how much use it will be to go through it perfectly, but if I read out what it says here, there's an image segmentation step, an object convolutional positional analysis step, large window and small window CNN model training, large window and small window model CNN model inference, and a fusion decision, which is what I was just saying in terms of if you get lots of patches representing an object, you need to make a decision about how to combine those. But the important thing in here is this part, which is, I don't know if you can see my cursor, which basically says that there's the concept of a small image, a small patch and a large patch, this was an important component of the method. So this illustrates the kind of detail that we were prepared to go into, and some of this would be criticised for being handcrafted, I guess, but nevertheless, we were able to fit, if we could identify individual objects, we were able to fit a moment bounding box around the object, and that gave us information about that object. For example, what's the center of gravity, and also we were able to work out if it was a long, thin object or whether it was a compact object, and that was important in this decision to apply either a small window or a large window. We could also sample across a long, thin object and determine some locations based on the sort of the central long axis and cross sections across the object as to where we should be placing the patches for input to the CNN. So yeah, that can be criticized because there's a lot of sort of handcrafted stuff going on there, but it does make it does fit with what's required in terms of the objects that you might find within a remotely sensed image. So we had two study sites. One was Southampton, where I used to work, and one was Manchester, which is a little bit closer to Lancaster. We had, in these two study sites, Southampton and Manchester, we had about 10 or 9 land use classes that we wanted to predict. And I'll just show you what those look like. So things like high density residential, medium density residential, commercial and industrial, and highway. These are American terms. I don't know why we don't use British terms, but there we are. So commercial and industrial, notoriously difficult to separate. You can see why. There's railway, which means the railway track, not necessarily everything around it. Parking lot, park and recreational area, redeveloped area, which has had buildings taken down, and harbour and seawater. So these are extremely difficult things to predict, and we can see immediately that they're high order representations. So a CNN would be appropriate for the prediction of these. And the land use classes in the second Manchester study site are very similar. So this gives an example of what the application of the method does. We fit a moment bounding box around the object. We can work out that it's a compact object. We put the center point based on this moment bounding box. We can identify that very strictly, and we then put a large patch in this case around that object in order to be able to predict it using a CNN. Where the object, this blue line here, is identified to be long and linear, then we're able to fit the moment bounding box that tells us the nature of the object, and we can find the center points of these patches along the object, and that gives us multiple sources of information that we can then collate and make a decision about. This shows you the difference between the large window CNN and a small window CNN, which is 128 pixels on the side or 48 pixels on the side. The usual CNN type of convolution and pooling layers in sequence, and then a max pooling layer and an output. And this illustrates the results. So what we've got here is a benchmarking comparison in the traditional engineering research methodology sense of we've got an input, and then we've got alternative methods, 3 alternative methods. Markov random field, this means object-based image analysis. So basically, we've applied something like e-cognition segmentation to this, and then applied a support vector machine, SVM, to those objects. a pixel-wise CNN, which just means that we have an overlapping window or patch that runs across the whole set of pixels and applies a prediction based on the pixel. And that's what we really objected to be honest. Just as a reminder, going back to what drove the questions that we asked in this research in the first place was an objection to this pixel-wise application of CNN. There was a heck of a lot of this that was occurring in remote sensing at the time, and it just felt completely the wrong thing to do. Then we've got the method that we've proposed here, OCNN, which combines the large and small windows depending on the nature of the object, and then direct application of a small window or a large window. And you can see for study site 1 here, the result, if you compare it to an MRF, look at this red area here, you can see gradually that we're getting better, more accurate prediction of those areas. And this is a sort of comparison across those different classes and shows the overall accuracy of 89.52% and kappa of 0.88. So the main message here is the items in bold are the ones that are the most accurate, and the approach that we developed was the most accurate in all cases, considerably so relative to the 3 benchmark methods. This is the result for the Manchester study site, and you can see again the gradual improvement. So if you take this area here, for example, which is in the ground reference is a sort of canal or waterway, it's gradually it's misclassified at some places and then eventually is correctly classified through the method that we're proposing. Again, the most accurate method. So in summary, and I'll just speed up a little bit because I am running a little bit behind time. Remote sensed images contain objects. CNN images are patch-based. Sorry, CNNs are image patch-based. We developed an OCNN, an object-based CNN suitable for remote sensing that has increased accuracy, plus it retains the object boundaries, unlike the original traditional CNN. So that, in a sense, that's a precursor to case study 2, and case study 2 is more important. It's the one that I really wanted to talk a little bit about, and I'll just take 5 minutes to do that. So the problem statement here is that remotely sensed images contain land cover and land use information and higher order representations. What I mean by higher order representations is, so land cover could be something like grass and building. Land use could be urban, which would be a mix of those two things in a particular arrangement and pattern. And then a higher order representation could be something like a train station, which is a complex, much higher order, ontologically higher order representation. So all of that information, the building blocks in order to predict those things exists in remotely sensed images. But what's important is that they exist in an ontological hierarchy. And we'd already developed this suitable method for land use prediction. So the question here was, can we exploit this hierarchy in order to predict land use and land cover simultaneously, jointly, and to do it such that the prediction of one enhances the prediction of the other, and vice versa, and go back and forth. And the suitable method for doing that would be, in statistics, would be joint distribution modeling. But different than JDM in statistics, as it's usually applied, one of the properties here needs to be, it is a higher order representation, and therefore it needs to be predicted via deep learning or a CNN. So the idea here was to simultaneously predict land cover and land use, and to use deep learning to predict land use and not to predict land cover, because land cover is a lower order state that doesn't require a higher order feature prediction. So we published this paper, which I'm really pleased with, called Joint Deep Learning for Land Cover and Land Use Classification in Remote Sensing Environment in 2019. And this was done jointly with people in Southampton University and also with people at the Ordnance Survey. And Suzanne was the PhD student who led this, and he was working jointly with the Ordnance Survey. So I've put Ordnance Survey at the top of this set of slides here to illustrate that. And the two people at Ordnance Survey are Isabel Sargent and Andy Gardner, who are authors on this paper. So joint distribution modeling is basically represented by this this slide, which basically Suzanne obtained from Wikipedia in BASIS and then augmented it to put land cover classification and land use classification on the axis here. But basically the idea is that you predict one of these variables, and then you basically create a marginal distribution from which you draw a value of the land cover side, and then having done that, you can create a marginal distribution for the land use and back and forth iteratively until the solution converges. So that's what's represented here. In the interest of time, then I'll just move on to this illustration, which is a little bit clearer. The idea is that we used a multi-layer perceptron, or MLP, to predict the land cover, which is the low order state. And then we use that information together with the remotely sensed raw imagery in this object-based convolutional neural network deep learning prediction method to predict the land use result. And then we use the land use result in the MLP to predict the land cover result, and we use the land cover result to predict the land use result, and so on, borrowing information from both sides in an iterative fashion to converge to a solution. And the important point is that we're only really doing these two here, land use and land cover, but this method is readily extendable to higher order functions, such as to predict the golf course, train station, etc. So the same two study sites, and I can thankfully go through this very quickly now, the same land use classes, more or less, for the study sites. The land use prediction is done via a convolutional neural network as before, but this time it's 96 pixels. And then the result is shown here. So interestingly, the number of iterations that was required was small. That bothers me a little bit, but the concept, as I said, is more important than the actual implementation in this case. So that there's room for other people to come in and think about the rigorous implementation of this as a concept. But the concept we wanted to get out there. For this image subset, you can see basically red means that it's not very good prediction, and then iteratively you move forward to these yellow. Yellow means that it's more accurately predicted to a satisfactory level. So there's definite improvement as you go through the iterations, and as land cover and land use, it's reinforcing each other. So here you can see, for example, that this is land cover. All of this is land cover in this slide. The land cover is pretty noisy here in iteration 1, but as you go through, then it smooths out and you get a much more pleasing representation. This is the equivalent for land use for study site 1. Again, the land use starts off pretty variable, and then it smooths out and you get a much more pleasing representation. This is for study site 2. I won't go through it because, well, you can see again, if you take this water body, you can see again that there's a sort of improvement through time, through the iterations, not time. As you go through the iterations and it converges, then eventually you get the correct prediction for that water body. And this is the most important slide in the whole talk. This is the one where Suzanne presented this actually at the Ordnance Survey, and I fell off my chair because to me this was a tremendous result. That within about 10 iterations, the model has converged. So you see that you get convergence beyond 10 iterations, but through the first 10 iterations, you get a sizable increase in the accuracy. And let's just break this down. So the blue represents land cover for study site 2, and the green represents land use for study site 2. So you start off here at iteration 1 with the result of applying deep learning for land use prediction, and here, sorry, land use prediction at about 78%, and the blue land cover starting off at about 82.5%. If we apply the MLP. So when we apply the CNN directly, using the method that I introduced in the first case study, we get an accuracy of about 78%. That's deep learning. What we then do is increase the accuracy through iteration by borrowing information back and forth in this ontological hierarchy between land use and land cover to get to accuracies that are far higher in both land cover and in land use. So to me, that was a remarkable result. And then I knew that we had something that was very special. Yeah, and if we compare the standard MLP, SVM, and the Markov random field approach to what we get with joint deep learning for both study site 1 and for study site 2 in the blue and the red, you can see the sizable improvement in the accuracy. So I was really pleased with that result, and I do believe that because it's so obvious now that you know it, that land cover and land use are locked in this ontological relationship, and this method exploits that ontological relationship and leads to very large increases in accuracy. It's so obvious. I believe that it will be picked up and applied widely in remote sensing. So in summary then, representations, we shouldn't neglect them. They're key to geospatial data science, and we must go beyond analyzing the data, as Peter Diggle implied. And for these 2 case studies, object-based deep learning model is appropriate for remote sensing. There are obviously innovations occurring all the time in terms of machine learning that are very interesting, and some of the stuff like attention, multi-attention networks are really interesting at the moment. So there's a lot going on, but in a conceptual sense, that was found to be useful. And then this joint deep learning concept, which addresses this long-standing land cover land use duality, I find very interesting. And of course, the most important point probably is that it can be extended easily to hierarchical ontologies. So, we can go beyond land use up the hierarchy. So, most important point, Zhang was the student at the time, now lecturer at Lancaster University, who was undertaking that work, and listed here are the different co-authors on that work. Thank you very much.
Thank you very much, Peter. That was a really fascinating talk. We've already got a question. So great talk. I learned a lot, thank you. I'm wondering, can you comment on the spatial resolution of the data these models can support, and how scalable the models in terms of national or global scale classification?
Well, I think the idea, part of the motivation in the development of those techniques was fine resolution remotely sensed imagery. So we were thinking of sort of 2 meters, 5 meters, that sort of resolution to start with. But it's not the resolution that's necessarily important, of course. It's the relationship between the resolution and the things that you're interested in that's important. So it's the interaction that's important. In other words, the things that are out there in reality or phenomena have a particular sort of natural scale to them. And if you're interested in those things, then you need to choose a resolution that interacts them in such a way that the data give you the support for your questions that you're interested in asking. So it's not the resolution per se, it's the interaction between the phenomena and the resolution that's important.
Thanks. Another question's come in. So it's, were existing land use datasets covering the study areas used in any way, e.g. For the machine learning, or to compare existing datasets used in practice, the results from your methodology? And which classifications were used?
In terms of creating the training data?
I assume so, yes, in terms of, yeah, the training data.
Yeah, I think that would really be a question for Zhang to answer more precisely. But my understanding was that the training data were created using Google Earth imagery, so done manually. Yeah. For those small study areas.
I've got a sort of a similar question, really. So, at the moment, you looked at UK data.
Yeah.
There's already a lot of data on land use in the UK from other sources. So for instance, from VGI sources or open sources. Whereas there's very little data in the global south, for instance. So this sort of methodology would be really applicable to cities in the global south where there isn't really any other types of data. So how would your methodology work with sort of informal settlements and those sort of land uses that you're finding in
I was trying to big up the approach and say that, you know, it's an interesting concept, and people should have a look and see if it's applicable, etc. What mitigates against that enthusiasm really is that well, let's go back. In the year 2000 at ITC in the Netherlands, I made the provocative statement that nobody will be doing hard classification in the future. Nobody will be doing proportions estimation in the future, you know, like fuzzy classification, etc. Everybody will be doing super resolution mapping or subpixel mapping, because basically you can get more information than otherwise. In other words, it's a superior approach in terms of information retention from images. And of course, it didn't happen. Of course, because people are going to use standard available tools that they can pull down. And if you know, there's an access issue, there's an ease of use issue, etc. And there's also the issue about understanding what's going on there. And so the method may suffer from the same kind of issues and problems in terms of its uptake. You know, like unless we provide the software so that people can do it, pull it down, as with geographical weighted regression that the team there with Stuart and Martin and others and Chris, you know, put out some cheap software that facilitated access. That's so important in terms of the uptake of a particular technique. So unless we produce those, make the code readily available, then we can't expect for people to really pick it up. But to answer your question, in any scenario, the question that you have to ask yourself is: do you really want land use and land cover? I mean, probably, and I hate to say it, probably you don't. Probably you just want a land cover map. So are you going to go to the trouble of predicting land use in order to enhance your land cover map and then throw away the land use map if you're not really interested in it? And I think that's an important question really about uptake. Okay, but the fact that we can do it, and there's a and the fact that it's conceptually strong, I think is at least a starting point.
Okay, we've got lots of questions coming in now, which is great. So,
good.
William has asked the sort of phrase from Peter Diggle: don't analyze data, analyze problem. Would Peter Diggle disapprove of the creation of data scientists, i.e., specialists in data analysis, but without a thematic discipline to contextualize the analysis?
Yeah, I can't speak for Peter, obviously. Peter is a statistician and is coming at this from a statistical point of view. But I think, in part, the motivation is as is commonly the case in statistics, to start with a problem and allow the problem to motivate the design that follows. For me, that would be the important thing. In terms of data science, I think it's really. I think in the context of data science, I think that statement is really important. There's so much stuff that's being done, but is it right? You know, is it principled? Are we forgetting principles that we've learned over the last 40 years or so? You know, where have those principles gone? And you know, what value can bringing those principles back to the fore and starting there and you know, adapting the techniques that are coming in so that they do fit with what we know as a community, you know, what we've learned as a community. Do you see what I mean? So I think Peter's statement's really important, actually.
Another question from Nick: does the increase in accuracy justify the effort and more complex modelling employed? So diminishing returns, I think.
Well, I would say yes, and usually with these kinds of things, you kind of don't bother, but before you know it, they're mainstream. And I'm not saying that this particular technique will be mainstream, but I have seen over time things. I remember saying in something like the year 2000, a guy called Steve Gunn in Southampton, wouldn't it be interesting if we adapted the it was an MLP at the time, adapted the MLP so that it had a spatial sort of array, so that we could drop patches of images directly into the MLP, and we never did it. But it's that sort of thing that you know, you think it's a small thing, but eventually these things become really, really mainstream, and it's mind blowing. You know, so what seems niche early on does become mainstream before you know it. And so I would say yes. It's not quite an answer to Nick's question.
No, not quite the next question. But you know, you have to try these things out to gauge what, you know, when do you stop? You know, what is an optimal what is the optimal or satisfactory solution?
I mean, by the way, while I mentioned it's handcrafted in the design, but it's not handcrafted in the implementation. It's automatic. It's just the training data, like every other technique that required to drive the method.
Right. Okay, we've got another question from Daniel Lewis. This is sort of similar to one I asked, which is about the context of your case studies. So both your case studies were urban. Would you anticipate similar success with rural land cover uses?
Good question. That's a really good question. I think it depends, obviously. I think it depends. Really good question. And of course, most of the world is going to be rural, so it's an important question to ask. I think probably there's less going on, so there's less complexity. So I suspect that the advantages in terms of exploiting the ontological hierarchy will be less. Yeah, then there may be a one-to-one mapping between land use and land cover, which would then the advantage sort of evaporates. So if the agricultural fields are large, like they're 1 kilometer on the side, and you're interested in what's the land use within there, well, it's agriculture, and what's the land cover? No, that's not true. So what'll happen is the agricultural land use class will cover several land cover patches, which are the agricultural fields, and then the advantage will exist. Yes, it'll still work.
Good. Christopher's asked, have you tried using scale space methodology to determine the optimal scales for your CNN analysis?
Similar, yes, we have. We published a subsequent paper which is called Scaled Sequence OCNN, or Scale Sequence Joint Deep Learning, sorry. So SSJDL subsequently, which is similar. I think it's not quite the same implementation of the approach that's being mentioned, but it is related to that. We acknowledged that there was an issue, and in order to try and find an optimum in terms of the size of the patches, we implemented a particular method. The unfortunate thing about that method is that the space of possibilities is smaller than the true space, so you're not exploring the space fully. But yes, we did try that.
Final 2 questions, both from Phil Barty. The first one is about augmenting your input data. So you said you used Google Earth and you manually classified it. Did you think about augmenting it with such things as OS Master Map, which has land use classifications on it, such as?
We didn't yet, but that would be a great thing to try, especially as the work was done jointly with the Ordnance Survey. Obviously, if you're segmenting and you want that to be general, then across the globe, then you would use a particular any particular type of segmentation algorithm. But if you're in the UK and you've got master map, then of course you could use those objects as a starting point and try and allocate classes to those. Plus, as you mentioned, Scott, there's some prior information there also. So you could be looking at change, for example, based relative to that.
And I think the final question from Phil is it's an interesting one. It's to do with at what point does this become too complex for you? Does the new deep learning models become too complex for universities in terms of the computational power and the resources that are needed? And when will Google, Microsoft, or Amazon take over this sort of research? Or is it just collaborative research you're looking at that point?
Well, that reminds me of when I walked into a colleague's office in in Southampton, and they showed me Google Earth, and I thought, blimey, what on earth is going on? I'm out of a job. Mind you, my good child did tell us several years before that was going to happen. I'm not sure about the computational. I mean, the university is pretty well endowed with computational resource in terms of high performance computing, etc. Maybe not so much on the servers side. Not sure, but it's an interesting point. Certainly, well, I mean, there's research going on to in part to make algorithms efficient. So things like multi-attention modules within networks are designed in part to focus attention on what's important, but also, of course, to gain efficiency so that there's less redundancy in the prediction. So there's always going to be a trade-off there, isn't there?
I suppose it's to what extent can this research be monetized? You know, so in what extent would Google, Microsoft, and Amazon become interested in doing this sort of thing, and it'd be all about making money? So,
not for me.
Yeah, so, on that cynical point, I think we'll wrap it up because we're 5 minutes over. So
yeah, brilliant. Thanks, everyone.
Thank you very much, Peter. It's been a really interesting talk and some great questions. So thanks for joining us this lunchtime.
Brilliant. Thank you.
And speak to you again.